Okay, so for this last video for this section, let's just practice some conceptual understanding of these notions of span. So I'm going to do a formal proof down below for anyone that has taken Math 3000. That's great. We're going to work with a proof involving set equality. If you haven't taken Math 3000, don't worry about the formal structure of the proof, but hopefully following the logic of the proof will convince you that this statement up top is true. So the statement we're trying to prove is let's consider vector v1, v2, v3, and w. These are four different vectors in Rn. And what I want to prove is that if vector w is in the span of v1, v2, and v3, then including that vector w along with vectors v1, v2, and v3, the span of that set of four vectors is going to be the same as the span of the original three vectors v1, v2, and v3. So let's prove this statement down below. So let's start with our given information, which is that w is in the span of v1, v2, and v3. So that means I'm going to take this vector w and I can write it as a linear combination of vectors v1, v2, and v3. So I can write it as a times v1 plus b times v2 plus c times v3, where a, b, and c, these all denote constants. Okay, and before going further, just want to motivate how this proof is going to work. So this is a set of vectors in Rn, and this is a separate set of vectors in Rn. And what we want to prove is that these two sets of vectors are equal to each other. So in other words, if I have any vector in this span, it has to be in this span, and vice versa. Any vector in the span of these three has to also be in the span of these four vectors. Okay, so then let's consider some arbitrary vector. I'm going to call this u, which sits in the span of vectors v1, v2, and v3. So I'm going to start with a vector over here, and I want to prove that that vector is in the span of v1, v2, v3, and w. And so this direction is pretty quick to show, and that is, since u is in the span of v1, v2, and v3, that means it equals x1 times v1 plus x2 times v2 plus x3 times v3. Thus, that means we can write it as 0 times the vector w plus x1 times v1 plus x2 times v2 plus x3 times v3, where x1, x2, and x3 are all constants. So this would tell us that this vector u sits in the span of the vectors w, v1, v2, and v3. And let me put my arrows above each of those vectors. So then let's take a vector, an arbitrary vector, and we'll call this vector, to differentiate it from the previous one, u2. So now I want to prove that u2 is in the span of the vectors w, v1, v2, and v3. Well, this means then that u2 I can write as a linear combination of these four vectors. So I can write it as some constant d times the vector w plus some constant y1 times v1 plus y2 times the vector v2 plus scalar y3 times the vector v3. And this is going to imply then that u2 can be written just with some regrouping of terms. I'm going to replace w with our assumption. We knew that w is in the span of v1, v2, and v3. So I'm going to replace this w with our assumption that it can be written as a linear combination of those three vectors. And then I still have my y1, v1, y2, v2, y3, v3 at the end. And so now I'm going to rearrange my terms. I'm going to distribute the d through each of these and then group my v1 terms. So in other words, I can write this vector u2 as the scalar a d plus y1 times v1. So I'm going to group all those terms together, plus d times b plus y2 times the vector v2. And then finally, plus d times C plus the scalar y3 all times v3. So now I've written u2 as a linear combination of v1, v2, and v3. So now I know that u2 has to sit in the span of v1, v2, and v3. So now I've shown that if any vector is in the span of w, v1, v2, and v3, then it has to be in the span of just v1, v2, and v3. So now we know that these two sets are equal to each other.